Hi everyone, my name is Matiu Rahman and I am from University of Virginia. I am glad to present our research flash, a comprehensive approach to intrusion detection via provenance graph representation learning. This work is in collaboration with Hadi Ahmadi from Corvic and my advisor Wajul Hassan from University of Virginia. In recent years, we have seen a rise in the number of highly sophisticated cyber attacks known as advanced persistent threats. These attacks are targeting big organizations and governments, and they are causing high financial losses. According to the IBM data breach report in 2023, the average global cost of an APT attack was $4.45 million, which presents a 15% increase over the previous 3 years. Moreover, 97% of the organizations are facing an increase in cyber threats since 2022. And these threats are highly stealthy, with the average life cycle of an attack being 277 days from identification to containment. To detect these APT attacks, researchers have been building provenance-based intrusion detection systems. So these detection systems, they rely on system audit logs in order to capture various system level activities. And then provenance graphs are constructed from these logs in order to model the causal relations between different system objects such as process, files, and network sockets. So the nodes in these graphs represent system entities, and the edges presents the system syscalls. The existing provenance-based detection systems can be broadly classified into three main types. The first one is the rule-based class of systems. So these systems work by requiring non-attack signatures. However, they are vulnerable to zero-day attacks vulnerability, meaning that they cannot detect new types of attacks without pre-existing attack signature. And crafting rules for these type of systems requires effort. The second type of system is the learning-based graph level systems, which detects anomalous subgraph from a given large provenance graph. However, these systems generate very coarse-grained alerts which are not very helpful for the analyst in pinpointing exact system attack entities. The third type of systems are the learning-based node edge level systems. So these systems addresses the issue faced by the previous two classes of detector by generating fine-grained alerts and without requiring attack signature. However, they themselves suffer from some key challenges such as low operational efficiency and generating high false alarms, which directly affects the practical usability of these systems. Our proposed solution to deal with these challenges is called Flash. So Flash is an anomaly-based node-level detection system capable of detecting zero-day attacks. Flash achieves high detection accuracy and operational efficiency for timely and accurate APT detection. The main insights behind Flash for dealing with the challenges of high false alarms and low operational efficiency are that high false alarms can be tackled through the use of semantic attributes in provenance graphs, which can greatly improve the system behavior modeling, thus reducing these false alarms. And for the low operational efficiency, we observe that the efficiency of graph representation learning, which is widely used in existing PIDS systems, can be improved through a novel embedding recycling technique used in Flash. So during the training phase, Flash takes the system logs and converts them to a provenance graph. Then Flash uses a semantic word-to-vec encoder for encoding various text attributes present in the provenance graph, such as file names, file paths, process names, network IPs, etc. Then in the third step, Flash uses these semantic features for training graph neural network model in order to capture the surrounding neighborhood structure around each node in the graph. These structural embeddings are then stored in a database for use during runtime. Then Flash uses the semantic features and the stored structural embeddings for training the lightweight classifier model. For efficient real-time threat detection. Then for the detection phase, Flash takes the incoming system logs, converting them to a provenance graph, and using the pre-trained word-to-vec model for semantic featureization. Using these semantic features along with the stored structural embeddings, Flash runs the lightweight classifier. The lightweight classifier detects anomalous nodes and it raises them as alerts, which can then be analyzed by a security analyst for potential threats. So I will go over the main components of Flash training phase. So the first component is the provenance graph construction, where we take the audit logs and convert them to a provenance graph. Flash applies a set of pre-processing techniques to simplify the graph. So these include merging multiple edges of the same type between two nodes and removing non-persistent execution-specific information from the node attributes. Then the second component deals with solving the challenge of semantic and temporal information neglect in existing PIDSs. So audit logs contain rich semantic attributes about system entities such as process name, file paths, etc. And these attributes have been neglected in the existing node level PIDSs, which directly hurts the detection accuracy. So word2vec is an unsupervised technique for encoding these text attributes into vector space or embeddings. However, the problem is that the vanilla word2vec does not preserve the words order in a sentence, which, as I will explain, is important for capturing the temporal ordering of events in audit logs and in the provenance graph. So for temporal semantic featureization, Flash first constructs a causal sequence using temporally ordered node events and attributes which it has with its neighbors. And then each word in the sentence or sequence is encoded into vector space using a word2vec model. Then for capturing the temporal information between events, Flash uses a positional encoding scheme to combine these word encodings into temporal ordering aware feature vector for our anomaly detector. So for encoding the graph structure around nodes in the provenance graph, Flash uses a graph neural network model. So specifically it uses a graph say GNN model for encoding this structure. This model utilizes the word2vec semantic encodings produced in the previous step as node features for our GNN, and it follows an unsupervised training technique to learn the node embeddings. However, the problem here is that the use of graph representation learning through graph neural networks is slow, and it comes with significant computational overhead. Because the iterative message passing for encoding graph structure can increase the computational cost with larger graphs. And existing optimization techniques such as subsampling or sparsifying large graphs can cause information loss, which will directly hurt the detector's detection performance. So our solution to this is the GNN embedding database. So many nodes in the provenance graph, they maintain a consistent pattern of behavior, meaning that their graph structure remains static over various execution runs. So we can store the GNN embeddings for these nodes as key value pairs to speed up inference. So the keys in the database represent the node identifier and the values represent the GNN embedding along with the neighborhood set of the node. Then during the detection phase, the main concerned components of Flash are the GNN embedding database and the lightweight classifier for alert generation. So I will go over how Flash attributes stored embeddings from the GNN database during runtime. So for a given node, Flash first extracts the current and stored neighborhood context during runtime from the database. And then it uses the Jaccard index matrix to compare these sets. And if the Jaccard index matrix equals to 1, then Flash uses the GNN embeddings, otherwise it relies on the semantic features for anomaly detection. So the lightweight classifier for alert generation takes as input concatenated word2vec embeddings and pre-stored GNN embeddings. from the database. Then it performs the task of classifying nodes into their system types and identify anomalies as misclassified nodes. So the intuition here is that the model was not able to classify these nodes correctly because it has not seen these patterns or behavior during the benign phase of the system, and thus it raises alerts for them. For evaluating our system, we used 4 audit logs dataset from DARPA and the research community, namely DARPA E3, DARPA OPTC, StreamSpot, and Unicorn. We evaluated the attack detection performance of our system and compared it to the existing node level system called ThreatTrace. And Flash achieved better performance in comparison to ThreatTrace, achieving higher precision, lower false alarms, and better F-score. We also evaluated the attack detection performance of our system on a graph level granularity and compared it to the graph level system called Unicorn. And again, Flash achieved superior detection performance in comparison to Unicorn, achieving better precision, recall, and F-score. We also conducted experiments to evaluate the operational efficiency of our system and compare it to the existing node level system called ThreatTrace. So we found out that the use of lightweight classifier and embedding recycling enabled Flash to achieve up to 3 times speed improvements in comparison to ThreatTrace. We also evaluated the runtime resource overhead of our system, and we discovered that the Flash utilizes minimal system resources for threat detection. We conducted many other experiments to evaluate the efficacy of our system. So these include the impact of key parameters and components like effect of audit logs, batch size on detection and runtime performance, comparison study of various downstream lightweight classifiers, effect of temporal word-to-vec encodings, and efficacy of GNN embeddings. We also evaluated the robustness of our system to adversarial mimicry attacks, and we found out that the Flash is resilient to these mimicry attacks. So in conclusion, I presented Flash, which is an anomaly-based intrusion detection system working in an unsupervised manner without requiring expert knowledge or attack signature. Flash achieves high detection accuracy through the use of semantic embeddings. Flash generates fine-grained node-level alerts to help the security analyst locate exact attack entities. And Flash is highly efficient through the use of GNN embedding recycling technique to achieve high efficiency for detecting threats in real time. Thank you for your attention. For more information, you can reach out to the mentioned email. Our code and paper is available at the showcase link.